Okay, awesome. So this is group 10. Take it away, guys.
Good afternoon, everyone. We are going to be presenting our project today. We are Group 10, otherwise known as Rapid Launch, and our project that we'll be presenting is the Satellite Springer. A quick introduction for everybody that's going to be here. The team is comprised of 6 individuals. That's going to be Oren Anderson, Adam Hayes, myself, Ryan Arake, Brandon Stoles, Adam Peroff, and Ryan Gorman. We are all from a mechanical engineering background, but we have areas of expertise outside of mechanical engineering that we've used to apply to this project and for the development of it. Just a quick agenda for what we'll be covering today. We'll first be covering a product overview, how it works, and then we'll be covering our 5 subsystems: the door, the launcher, the rails, the container, and the electronics. And then finally, we'll round it out with just a quick estimation of what the cost for both a prototype and a full production model of our project would look like, and the conclusion for why you should pick the Satellite Springer.
All right, so here's our hedgehog concept. The idea is that simplicity through innovation will allow us to make assembly quick and reduce cost. Basically, by doing innovative techniques that allow our assembly to use less parts, like slotting parts into others in almost like a puzzle piece fashion versus like using bolts for everything, or anything else similar to that, we're able to reduce the part count and the assembly steps. So our passion is simplicity, and that allows is inherently economic. And we're going to be the best at the world in device reliability because of our simplicity, basically. So if we go to the next slide, here is the sort of the overview of the Satellite Springer. On the right, we see the full outside of the Satellite Springer. And on the left, we have a small GIF of the door opening and the CubeSat exiting the satellite canisterized dispenser. So on the next slide, we see the different subsystems. So we have the door, the launching mechanism, the guiding mechanism, the container, and the electrical connections. The door analysis was done by Adam Peroff and Adam Hayes, and Adam Peroff will take it off from here.
Yeah, so here you can see our door. And as you can see from the picture on the left side, we have 3 spring hinges. And one of our features is the magnets that are on the hinges that slow down the door after the CubeSat is released and prevent it from bouncing back and damaging the CubeSat. And then also on the right, we have a latch, which is released by a solenoid, which allows the door to open. So here are the 2 customer needs that pertain to the door subsystem, customer need 18 and 2. And here are our justifications for why our door excels in these areas. So for customer need number 2, the door needs to survive the worst possible structural loads. So the G-force is 7.5 Gs. And as you can see on the right side, we have the locking mechanism, which deals with the preloaded tension rails pushing against the door. And basically this locking mechanism takes the force and amplifies it and translates it vertically so that it locks the CubeSat into place, so that the CubeSat will avoid the forces and vibrations during launch. So here we performed dynamic analysis on the door modeled as an idealized beam. And on the right side, you can see our shear force and bending moment diagrams. And we use these to calculate the acceptable deflection, which was the deflection, which was 0.5 millimeters, which is an acceptable amount. And we also determined the thickness of the door, which is 3.5 millimeters. And this ensures that the door creates a strong seal and can withstand the forces. So customer need number 18 is the time to open the door. And so we took the launching mechanism, which we'll go over its 4 springs, and we performed energy analysis and found the potential energy from the springs. And then we converted that into the angular velocity as the CubeSat is leaving. I mean, the angular velocity of the door as it opens. And then we basically just use kinematics to find the time to open, which is 0.117 seconds, which is significantly less than the 2 seconds required. So we excel in this need.
All right, so now it's time to talk about the launching mechanism. So for the launching mechanism, we use 4 springs, and you see that there's lots of what I describe as lightning holes that are for weight, but also for protrusions from the CubeSat. So the team that we were working with had non-standard protrusions from their CubeSat that would not be able to be accounted for otherwise without having a custom design. Fortunately, since this is a custom design, we were able to accommodate that. So that large center hole in the back is actually for a small thruster in their design that extends slightly past the launching mechanism plate. Additionally, the small asymmetry that you see is for a, what do you call it? The separation connector. The CubeSat separation connector, which I'll go into later on during the electrical analysis. So this particular customer need for this particular mechanism revolves around the CubeSat dispensing speed. So it had to be somewhere in between 0.5 and 2.0 and tunable to some extent. To do this, we performed an analysis on the next page that found the energy stored in the CubeSat before and after launch. So using conservation of energy, we were able to create a relation that gave acceptable spring constants and displacement values. These together allowed us to identify off-the-shelf springs and a variety of off-the-shelf springs to allow for various output velocities. Given the 24 kilogram estimation given by the customer, we find that for 1.5 meters per second, a spring with 544 Newton meters for the spring constant, and then about 0.2 meters of displacement gives us the velocity that we need. However, given that same information, and given that the CubeSat that we were working with is actually only 17 kilograms, it actually launches it at 1.78 meters per second, which is suitable given that they wanted us to launch it faster if possible. Other springs could have been selected, but these satisfied all the needs that we saw fit. All right, so for the guiding mechanism, a few different metrics had to be considered. We had to consider, the friction that the rails would induce on the CubeSat as it exited. So we didn't want it to have too much pressure on the CubeSat or something like that, because it might not allow the CubeSat to be released, lots of energy loss from the exit. And we also had to have them prevent rattling. So there's a certain amount of tolerance in the CubeSat, and there's a certain amount of tolerance in the device that we attempt to account for using a special wedge system. And we go into that in the next few slides. So the customer needs that we have here revolve around the worst case loading conditions. We designed it for 7.5 Gs in all cases as the worst case. And then additionally, we had the wedge mechanism that prevented rattling of the CubeSat inside the device. In addition to that, for acoustic loading, we avoided susceptible designs and left room for acoustic foam given other CubeSat designs that did not include that. Fortunately, the team that we were working with had included that in their design and didn't see much reason for us to go super in depth into that. And for weight conservation, we decided to leave room for the acoustics, acoustic dampening. All right. So this was an analysis that I performed using approximate values for the spring constants of the rails and dampening of the rails, and then a sum of sinusoids approximate to that of a sum of sinusoids for the forces given, I think, this sort of a spectral graph that I found a while ago, and I used that to determine what the forcing conditions were basically, and what the worst case G loadings were and stuff like that. Using that and an analysis I made in Python, I determined what would happen if there was no preload and if there was preload, and how much preload would really be necessary to avoid the worst case forcing conditions. So in the top graph, you can see that it's basically bouncing around a lot and would likely cause damage to the CubeSat. On the one below, you see a small transient from the analysis, but otherwise no bouncing around. And basically this validated our use of the preload in our design. So yeah, this was the graph I was talking about. Using this, we were able to determine sort of the frequency spectrum and the amplitudes of everything for that analysis. All right. Additionally, that clamping on the sides of the CubeSat is about 882 newtons. That force is, I think, was mentioned previously, but basically, given the coefficient of friction between the CubeSat and the CSD, we find that there's 176 newtons of force of friction preventing the CubeSat from rattling laterally along the direction of the exit. That's really important because not only is sort of there a geometric constraint of the door and the launching mechanism bottoming out at the very bottom when it's pressed all the way down, there is also a frictional force preventing the CubeSat from moving, basically allowing it to transfer more of the, preventing rattling in the device, basically. All right, and then Adam Peroff will take us from here.
So here you can see the container on the right side, and some of the features include the standardized mounting holes and the aluminum 6061 material, which is cheap. It is very light to help us reach the 5 kilogram weight limit, and it's very strong and durable, so it can withstand the necessary forces. Here are the 5 customer metrics that pertain to the container subsystem and our justification for why we excel in these metrics, which I'll go through in the next slides. So customer need number 2 is that the container can survive the worst possible structural load, which is 7.5 Gs. So on the right side, you can see the shear force and bending moment diagrams. And from that, we got the moment of negative 7.488 Newton meters. And we use that to get the yield stress, which is less than the yield strength of aluminum 6061, which validates that the material can withstand the worst possible conditions. And we were also able to use the 0.5 millimeter deflection to calculate the necessary thickness of the back panel, which is 0.8 millimeters. Customer need number 6 is that the container must be able to survive the minimum and maximum temperatures. So here you can see some math that we applied to determine the change in the force from the springs due to the different temperatures, negative 270 degrees Celsius and 85 degrees Celsius. And we determined that we originally had carbon fiber, which we determined would not be able to withstand these temperatures. So that's why we switched to aluminum, which is able to withstand these temperatures.
Just to be a little more clear about that, we had to switch from carbon fiber to aluminum because of the coefficients of thermal expansion difference between the aluminum body and the carbon fiber plates. we found that there was enough translation to where it was likely there was going to be some form of cracking or fracture. So we decided to turn it all to aluminum so that the coefficients of thermal expansion would all be the same.
So customer need number 7 is that the container passes the ventilation standards. And the ventilation standards that the volume over area of ventilation is less than 50.8 millimeters. So here you can see the ventable volume and the area, which we calculated. And we determined that the volume over area ratio is 44.034 millimeters, which is less than the 50.8 millimeters. So we pass and excel in this customer metric. Customer need number 13 is that the container can fit a 12U CubeSat, and all of our dimensions, height, width, and length are larger than the dimensions for a 12U CubeSat. And we also calculated the volume for the CSD and the CubeSat just to prove that it will be able to fit. And then customer need number 17 is that there won't be contamination in the CSD. And because of the minimum ventilation area, we will not have contamination in the CSD.
If you could go back a slide for just a moment, I just wanted to mention one more thing. Our CubeSat had some non-standard protrusions along the sides as well. So our volume, our inside volume is larger because we had to account for those. We also made it so that the door and the rest of the device had extra clearance to make sure that it was possible for those non-standard protrusions to be possible with our device. All right. So for the next slide, I want to talk about the electrical connection. So we use 2 different connectors. One of them is a DB9 connector that has flight heritage, so it will not have to be qualified, fortunately, given similar designs to previous ones. And we also have the separation connector, which is compliant with Rocket Labs. This allows us to be compliant with existing CubeSat designs, as well as the ones that were presented to us as part of the Aero design project. And in addition to that, you can see that there is some small holes for zip tying the wires to the back plate. That's really important for wire management. And fortunately, these are large enough to let air out of the device, but not enough to add any significant issues with contamination. All right, so there's several different customer metrics that we covered with this. Specifically, the electrical bonding and grounding requirements were followed. Basically, most of the materials that we used were electrically conductive, and this prevented the possibility of charge buildup, which is something that I believe can happen during launch. Additionally, we made it so that our electronics were compatible with 28 volts DC. This is specifically, we were able to do this by having a 28 volt to 5 volt regulator that would power our control electronics. There were additional electronics that would route the 28 volts through a switch that would turn on our door given the proper sequence of events given by the launch vehicle. And all those wires were also included in the design. Can you go back for a moment? Sorry. For the power up, anytime the satellite launcher can power up anytime due to there being no significant power draw, like there's no like large capacitors or batteries that need to be charged up. And that also means that there's no issues with it running for over 12 months. Nothing can discharge over time. Nothing can degrade over time. All right, so now at the next one. Basically, going over very similar things to that. And just to double check, yeah. So the specific controller that we used was a Arduino Nano that was powered by that 5 volts regulator that I was describing before. That handles all of the input checking, specifically. I think there are 2 door sensors to make sure that it cannot leave accidentally, basically, and other things like that. Basically, lots of redundancy, all going to the Arduino Nano, and that will do any digital signals processing that's necessary to figure out when it's time to let go of the satellite. All right, so that's that. Now it's time for Ryan A to back in.
So our remaining 6 customer needs were not ones that we felt matched any specific subsystem and ones that affected the CSD as a whole. These will be as followed, just going through and being able to attach the CSD to a launch vehicle. To achieve this need, we made sure to use a standard bolt pattern and bolt size, and we just made essentially a cheese board mounting system along the sides of our CSD, so that not only could the CSD be mounted to the launch vehicle, but the position it was mounted in could be adjusted as needed. One of the biggest needs was obviously the weight. Anytime anything goes into space, we need to make sure that we can minimize the weight possible. So our current estimations using the CAD and SolidWorks is that it is 4.45 kilograms, which is about half a kilogram below the 5 kilogram max allowed for this project. Especially when we need to launch the CubeSat. Need number 10 follows that we need to have compliance with center of gravity standards for all possible launchers. We did some research and pulled up guidelines and standards, and we made sure to follow this such that the CubeSat would have no problems getting out and the CSD would have no problems being mounted within the rocket. And finally, need number 22, there was very highly emphasized that we could not be releasing any debris into lunar orbit. No contamination from the CSD out into lunar orbit could be released. So we made sure to implement this into the CSD, and there's no current debris that can be estimated to leave the CSD. Going into the cost summary, we were allowed a budget of $500,000 for a full production model, and around 500 for an estimated prototype cost. This is a current breakdown for how we have it so far. And then just going into the raw materials, one of the biggest things we were able to simplify down from prototype and mass production was just what we were going to be using for the sidings. The mass productions are going to need aluminum, but for the prototypes, we were able to avoid using that aluminum just for the purpose of testing. Going into our final slide, the reason you should be picking the satellite Springer is going to be these 6 reasons as followed. We've especially mentioned how it was light. It's about half kilogram underweight, and it's both adaptable. It will fit the non-standard CubeSat design from the project we were given. We made it able to fit and work. We have synergy between all of our components and all of our subsystems, and we focused on simplicity in everything that we designed and we built. And for the cross-platform, we made sure to do a series of analysis for every possible worst case, so that not only would the CSD survive, but the CubeSat would survive and our mission could be performed successfully. Finally, we have the set and forget methodology, and this means that once everything is assembled, once everything is tested and works initially, it can be set and left and forgotten about for the 12-month period needed while everything else is completed. And as it goes into launch, that you can be confident that the CubeSat will be protected both from impact forces and vibrational forces that will affect it during launch. Thank you for your time. We now open up for questions.
All right. If you guys don't mind, I'll go first. So I just wanted to ask you guys about, I'll just start with the vibrational analysis. So you tell me a little bit more about that custom vibration setup you did?
Yeah, so
If you don't mind taking me to that slide too, so we have that as reference.
oh yeah. Ryan.
Yeah, I'm doing. This is going to be guide, right? That's where you wanted to
go to the page that I covered.
17,
that
I think.
Yeah.
Yeah.
Okay, so to go into a little more detail, I know we
Oh.
might have brushed over this a little too fast.
You guys can just leave it here. It doesn't matter. You don't have to go into
Okay.
presentation mode.
Yeah, so basically, using the standard sort of vibration equations of a spring mass damper system, I expanded on that analysis, basically making it so that the spring mass damper was like pressing against a movable object, as in the CubeSat, basically. And then I calculated the position of the CubeSat, which is what you see in that analysis. And it basically zeroing out is when all the forces are sort of helping the spring mass damper to like push the CubeSat against the wall. But when it's going all crazy, that's when the spring mass damper, which is the rails, the rails of the device, are no longer able to hold it against the wall, and that's why it's moving. So with enough preload on the springs that we use on the rails, we're able to reduce those vibrations down to basically nothing.
Okay, but the thing is that doesn't say anything about whether or not your CubeSat's going to experience resonance.
That's completely fair. Fortunately, the CubeSat team we were working with was confident that they also were dealing with the vibration analysis. They mostly just wanted us to prevent shock loading. And that was most of the goal of this particular analysis.
Of course, it's just that, even with a CSD also has to be able to survive the vibrational modes expected during launch.
Yes. Okay, yeah, I see what you mean now. Yeah, that's fair. Yeah,
so that's definitely, you need that as well, even if they're doing it on the CubeSat side, because when they do testing, they'll be testing with the deployer and the CubeSat inside, so together they'll have to survive. But yeah, definitely need that.
Okay, fair enough.
Juliana, do you have any questions?
Yes, I do. Okay, so a real good presentation. I like it. First question that I have, and I think Mark and I are gonna go back and forth. But so the first question is, can you go back to their door? And I think it was their customer needs as well. Yes, okay, here. In their need 18, you mentioned the customer metric is open 30 out of 30 times. So
to clarify that, that was because around 30 is statistically significant. And that this was adapted from the customer needs. This was our quantitative version of it. Basically, theirs was 100% reliability, and ours is basically, it has to work all of the times that we test it, up to 30 times.
Okay, so you have tested this or going to?
This is something that we would test.
Okay, all right. And then the next question I have is, when you're calculating the time it takes to open, and it's 0.117 seconds, so it's a very short time.
Yep.
Does that only count the time it has to unlatch basically for the metal, or does it also counts their that little semicircle the door has to make to actually open?
Yes, so that's going to be the semicircle that it travels.
Okay.
The time it has to unlock is probably a significant portion of that, but we were mostly considering that the actual time for it to open, because that's when the CubeSat would actually leave.
Yeah. Okay, makes sense. All right. So it opens pretty quickly. Yeah, go for it.
Yeah, it is really fast.
And in that case, since it opens that quickly, I didn't see that you guys had anything that was actually holding your spring plate back. Is your CubeSat pushing up against the door during when it's loaded?
Yes.
Okay. Any worries with the CubeSat possibly getting pushed out into the door?
Yeah, so that was a worry. However, that we covered that analysis. I don't know if we talked about it briefly, so I'll go into that in a little more detail. I don't know if we have that analysis somewhere in here, but go to the slide with the picture on it. Yeah, okay. So since the door opened so quickly, we had little worry of the CubeSat hitting the door on the way out. However, we did worry about about the door rebounding and hitting the CubeSat.
Which is why you have those magnets.
Yes.
My main question is just that, like, you've got a lot of force on the springs that's pushing the CubeSat. How quickly do those react? Because you showed like a nice animation at the beginning where you have the door opening and then the CubeSat releasing, when in
Yeah.
actuality it's releasing at
It
the
would
same
be somewhere in
time.
between. Yeah.
So, like, do you know have you guys gotten a chance to maybe take a look at if there's a possibility of your CubeSat losing a little bit speed by hitting the door, or is the door fast enough that just it gets out of the way before the CubeSat really gets launched?
Given when I did the analysis of the particular springs that we're using,
Mhm.
I found ones that had a lower spring rate, so it would be specifically over a longer throw, basically.
Okay.
Then I think we had been looking at some very short springs.
Okay.
So there was a worry of it losing some energy, but by using the longer springs, the rate at which it speeds, as well as the length over the energy transfer,
You're thinking
worry
that
about
there's
that
some
less.
chance. Okay. Well, of course, this will need testing. It's hard to do it
Yeah.
just off the block. But okay, so there you think that with your design it's going to be less likely. Okay.
And going off of your first question with vibration and this question with the door, the CubeSat's not actually butted up against the door as a whole. There is a like retention bumpers that are on the inside of the frame here that are difficult to capture in a picture. But there is some space between where the CubeSat sits and where the door is, and that's held in place with those bumpers. So when the door would swing open, it's not immediately chasing the door. It's going to chase that new space where the bumpers were.
Okay. It still would leave a chance to open, but I can understand
Yeah.
what you're talking about.
Okay, can you go back to the springs, please, and show them a little more in detail?
So these are the compressed versions.
Oh, okay, all right. Oh, and you have 4 of them. That's nice. Okay. Do you have the overall weight anywhere of all your
Yeah, if
assembly?
you go to the end, I believe it's 4.45 kilograms. I think we might have went over that slide kind of quickly. I think it's below that.
So
Yeah.
That's nice. That you saved quite a lot of weight. I wonder
Yes.
where.
So it was kind of funny. We did a fastener analysis, and we had originally been using M5s in a lot of places. And then we determined that M3s were completely suitable for most of the applications, and we saved like 0.1 kilograms just off doing that. Additionally, I did a lot of, what would you say, like pocketing almost on the faces. So the inertia is still quite high on the door. So I know we had mentioned like it has a certain thickness. I basically made the doors have an equivalent inertia to that thickness. So they're light, but also not completely solid.
Okay. And that actually brings up my next point. If you show me any, like their slide 32, I believe, actually, it would be nice to have the numbers of the slides somewhere so it's easier to refer back to them. But yes, 32, if you just click on this. How are you manufacturing that door and everything else?
So a lot of this would have to be with CNC machines.
Okay.
And for the prototype, that's not strictly necessary. You could do 3D printing for almost everything, honestly. But for a high fidelity prototype, you would have to do some CNC machining, or you could do manual machining and then just not capture all of the geometry perfectly. But that would be sufficient for a higher fidelity prototype.
So if I get this right, the whole CubeSat and not specifically the door, like that 3D cube shape, right? You're going to machine out?
Oh, I'm sorry. It's hard to see, but it's multiple parts. The render
Okay.
doesn't make the walls very clear. Let me oh yeah, go to that beginning one. No, the one right after that. Okay, so we have sort of a back plate, so that's going to be a large, like, flat machined part. And then on the left side, you have the door and sort of a door flange that goes around. Those are two separate parts also in flat plate. And then you have the rails, and the rails are bolted to those two flat plates. So there's 4 rails, and then there's going to be 8 bolts basically, and those are pretty hefty bolts. And we determined those through another analysis, but.
What about the whole container?
And then the walls are 16th inch aluminum.
But
So-
are
so-
they?
They're sheets. They're sheets. So each side, the right side does have a custom sheet, but the other 3 sides, the top, left, and bottom side, are all just 16th inch aluminum sheets that can just be attached to what the frame is going to be, which is just those 4 rails and the door and back plate. And those will just be attached on. And the idea is you, with the bolts, that you would just be able to easily remove those and access any interior mechanisms you would need to in case of emergency before you could just put it all together.
Okay, so then
So-
that means that essentially everything connects through the guide rails.
Yes.
Okay. That means that if you guys do take off the door, which you'll probably need to if a CubeSat has a remove before flight feature, which they normally should, that means that you can't, in assembly procedure, you guys can't torque or Loctite any of those bolts on that side before, because then you'd be removing Loctite when trying to take off that door. So
Can you explain
yeah,
that?
let me
why
go
can't
ahead
you
and
just
so
Yeah.
normally when you want to throw something into space, you're going to want to not only torque them well, but you're also going to want to throw Loctite in there as a secondary fastening mechanism.
Yeah.
And so when a CubeSat, which again, this is on the CubeSat side, they should have a remove before flight feature where that's used to ground it when it's not in the deployer, but once it's in the deployer, there's going to be other mechanisms for grounding the system, preventing it from turning on. So that remove before flight feature needs to be removed from the deployer. And so
Yes. Okay, so to be more clear, don't change the slide yet. These walls are completely removable.
but what are they connected to? How are they connected? If they're completely
Um,
removable, there's got to be a way you connect them, right?
Yeah, they connect to the
To the
rails
guide.
and the sides, but the rails themselves are connected to the front and back. So that can exist by itself without falling apart.
Yeah,
I
you-
know,
you
but
can
like you're
see-
still like those are bolts that are going through there, right?
Oh, you're
Those
saying
bolts-
those bolts. Oh,
Yeah.
okay.
Yeah,
Okay.
those bolts that you see along the edges in that render all bolt into the rails.
Mhm.
And then the rails basically bolt onto the back plate and the front. There's not a picture of it on this slide, but a front flange that goes behind the door. So then you could take off the side plates or the top plate and still basically have a frame, the full frame
Got it.
of
Okay.
the.
And by the way, are those guide rails threaded, or are they like
Those-
the
yeah,
holes for
those
the?
Oh,
Are they
I
threaded, or
believe
is it like
so.
an insert, or
sorry, these guys, like the going
yeah,
through
like the
front and
holes you're
back?
putting the bolts
Okay.
through?
Yeah, those ones they're all threaded.
All threaded. Okay, so again, just what I was saying was that if you're
Yeah.
using one of the sides of your CubeSat as a way to access it prior to packing it away, that means that during assembly
Yep.
procedure you have to do the torquing and Loctiting after.
Yep.
On that note, I guess we can continue. What material is your guide rails,
So the guide rails are Delrin.
Delrin? Okay. Have you guys taken a look at Delrin and any like outgassing, or just generally if it has been used in space before? Does it have space flight history?
Cannot speak to that.
Yeah. So since when it comes to polymers, important for you to know whether or not they have high outgassing characteristics.
It's not only
Because
that.
yeah,
Sorry.
there's
Sorry
one
to
other
interrupt
thing,
you.
and Juliana, if you want to continue the zip
Yeah.
ties.
Well, yeah, but I want to jump in on the Delrin. It's not just the outgassing that causes an issue, but Delrin, just like any polymer, and specifically, Delrin, they're polyoxymethylene, that's what it stands for. It is extremely susceptible to the UV light. It erodes like crazy, extremely quickly. And as we know, there is no protection against UV rays in space. So unless you're covering it with something specific or like some kind of coating and stuff, you can't really use it.
So-
Yeah.
Yeah, my question there is, would not the aluminum protect it? Like there's no window into it, so the UV light can't get into it.
We properly explained how it was assembled. So the actual guide rails themselves, this white piece that you see here is the only part that's made out of Delrin, and this is facing towards the interior corners of the CSD. The outside is just an aluminum mounting bracket
Yeah.
that's used to hold everything in place. So except for maybe a snapshot moment while the CSD is open, the Delrin will just be on the interior and won't actually be faced towards any direct exposure.
Okay, it could mean that then it might not be very reusable though, because once the door opens, you don't really have anything to close it, which means now it's directly exposed to UV
So
light.
the other thing there is like once the door opens and the CubeSat's released, our device is useless at that point. The CubeSat's already
Okay, it doesn't
exited.
need to have, it doesn't need to have reusability.
Nope.
No, we were emphasized it just needs to work once with 100% guarantee.
Awesome.
Yeah,
Cool.
in fact, we use materials in all cases that would burn on reentry, assuming this
Yeah.
were to somehow end
Yeah,
up
you
back
guys
on
aren't
Earth.
using titanium or
No,
anything like that that could have issues. So,
yeah.
but going back to those zip ties,
Mhm.
those are probably, what do you guys know what the material is for those zip ties?
Nylon.
That could have some issues if Juliana
Yes.
wants to detail that.
Yes, so nylon 6.6 has a very fun tendency. In their high temperatures, it gets viscous, and it gets high temperatures. The high temperatures, I mean, is 70 degrees Celsius, so it's not very high. And it gets very brittle and super hard in the low temperatures, and it's completely unusable when it gets to minus 270 that you've mentioned before. So in space, because of the influx of solar energy and etc., you are getting those flushes from high to low and high to low back again, your zip ties are not going to survive. Or at least I highly doubt that they will survive, especially if they get viscous at first, start melting around your electrical components, and then super brittle and hard and breaking those crimping points. So I'd suggest maybe think about something else, but zip ties aren't it.
Worst case, we could use metal zip ties.
That's
Also,
an
all
option,
of our
but-
cable does plan to be in a metal sheathing, just like a weave, just to protect it overall. So hopefully that will keep
Yeah, the
some
main
major
thing
issues,
is
but yeah,
to-
that is something to consider.
Yeah, the main worry is the wires getting in the way once the
Yeah.
zip ties no longer hold them in place. So
Yeah. Fair point.
I did realize I wanted to ask one more question about the springs from earlier. How do you guys attach your springs on either side of the spring? How do they attach to the plate and then back down to the?
Yeah, so this is something we struggled with for a while, like trying to figure out how to do this in a way that was elegant. What we eventually determined is that we would just wrap around like a very thin cable to each one, so that would prevent it from exiting. So it wouldn't like hold it together, but it would keep it inside the CSD basically. And since we don't need to reuse this, basically assuming everything's like pre-tensioned when we put it in, that is its own issue, and that would work fine. When it releases, the springs could hang out inside the CubeSat, but just retained using some very thin.
Right, okay, it could make testing very difficult,
Fair.
because if you need to set up for testing and put the CubeSat in and take it out, and now your springs are disattached again and you have to reattach them, could make testing very difficult for your CSD.
Fair enough.
Anything
I
else?
actually had another question, which was you've included vents. What was the reason behind that?
Yeah, so the NASA, one of the NASA standards for spaceflight has a ventilation area minimum, as well as sort of, for our case, a maximum, because we also don't want contamination. So we needed enough to let air out because we didn't want the device to pressurize during launch and possibly cause any weird issues as a result of that. So we just have a few small holes that the air can exit out of.
Sorry, can you say that again? You didn't want their device to, or you did want to?
Pressurize.
Okay, see. Yes, yeah, okay, that makes sense. Sorry, that was completely missing
Yeah.
it. Okay, that makes sense. Cool. Oh, on that note, have you made any calculations? And I'm probably stealing Dr. Traum's spotlight right now, but have you made any calculations on their temperature and specifically the steady state temperature inside of your CubeSat once it's lifted off?
No.
You might want to consider that, especially with the electronics, because they might freeze off if it's extremely low or start behaving weirdly.
Fair enough. For the electronics, we were also planning on basically encasing them in something similar to epoxy that has some issues. We have to identify a material that's going to work for that, but that'll prevent vibrations from damaging it and also prevent some of the heating issues, at least keep it stable.
Oh, and is your material for the door the same as material for the container outside? And can you show the picture of it again?
This picture?
Oh, like between the door and the opening?
Yeah, so this is perfect.
Yeah, okay. Yes, those are the same material. That has some issues with maybe cold welding, but we would basically grease all of the important surfaces.
Be careful
you
with
know.
greasing. Greasing could have oil, and grease has very interesting interactions in vacuums.
Really?
Yeah. There's like known things for like machines that are like they're made to work in vacuum, and you throw oil in there and it messes up the entire machine.
Okay.
You know, just if you are going to do something that's for greasing, you'd want to use something that's approved for spaceflight, or
Okay.
possibly put on some coatings to make that also could be a way of going about it.
Okay, sure. Fair enough. If we were to, I don't know if this is a time to ask questions too, but does anodization have issues with?
Nope, anodization is completely fine, though it can help with allowing for smoother movement, because it's the essentially what anodizing does is that it increases the hardness and helps
Okay.
prevent scratching of the surface. Most of the CubeSats are required to have anodizing on their rails.
Okay. Okay.
So I don't think it'd be anything different there.
Okay.
But if we can just jump to your cost real quick.
So at the very bottom.
So I noticed that you guys did not actually include costs for the actual engineers, as in salaries. You do also have to pay the people, just in general, like the people who are working on developing this, you'd have to pay them.
Okay.
Now you can technically spread this out, per Mark Worlds for free. You remember last semester, one of the teams was like, we'll just get volunteers. And
It was worse than that. They wanted to, I'm not sure that I should say this on video. They wanted to enslave nuns is what they wanted to do.
Yeah, I also know what group we're talking about. So in other news, yeah, you definitely do need to pay the people who are working on this. So you'd have to consider the salaries of the engineers and or whoever you'd assume was doing this. That'll definitely increase your costs a lot from the 87,000 you guys have right now. Not as important for the prototype, but definitely for your mass production costs, because that's going to be big time money.
Okay.
If you could just walk me through how you calculated the raw material.
Yeah, so the raw material was basically the way that we did that is we split up all the parts into their minimum square dimension, well, rectangular dimensions basically. And then using those rectangular dimensions, we would find places that would sell stock in at least similar sizes. Sometimes perfectly fitting it ended up being more expensive than just buying something that was slightly larger. So we would look around for stuff like that. One of the reasons it's so large for this prototype run is because of all the custom aluminum stuff that we have. Fortunately, when I calculated out for like 3D printing or something, it's far less. So I think the unit cost gets down to like 480 or something along those lines when I was looking at it.
Yep, okay, cool. That's what I wanted to hear. Now, the question is, from my experience, manufacturing and assembly costs, especially if you're grouping them together for the mass production, will cost you at least half of your whole raw material cost. At the moment,
Okay.
it's quite low. So I'm wondering if you have included tooling, if you have included paying for their place, for example, that you have to rent out the whole, I don't know, like a hangar to actually install the things. If you paid for, included the
A clean room,
energy,
probably.
that, for example, if you included their salary of the people who actually work on it, or like who actually have to manufacture / assemble, because at the moment this cost looks a little bit low, and those need to be included in the FDR. Sure, I know it's due today.
Yeah. I think who was doing the analysis? Maybe Brandon or
If anything, just consideration for the time period you'd expect this thing to be
Okay.
built. You don't necessarily have to be like, oh, I'm paying these guys for a year, but this thing's going to be built in 6 months,
Okay.
or something of that nature, just to, because it can definitely go up in time if we're considering,
Okay.
a lot
Sure.
of these components being made.
Sounds good.
Cool. I don't have any more questions.
And I have one last comment, which is not exactly about the presentation, but mainly about you all guys. Out of the whole presentation, which was about 35 minutes that we've noticed here, and the questions, I've seen and I've counted Oren talk about 2/3 of the way. I'm not exactly sure if that just means that Oren has done most of the work, but it sure does look that way when you're presenting it to the group. So when you're trying to present your whole design to their panelists or someone who, let's say, invests in it in the future, try to present it as a way, as a united front, as if everyone did the same amount of work and everyone can answer the same questions. Because at the moment, it doesn't look that way.
One thing I also want to ask about that is how do you prevent it from being like too much like back and forth?
Back
Oh,
and forth is-
when we start a conversation, you can't do much about that.
Oh, no,
But-
no. Like between like a team group, like if there's lots of switching going on, I guess practice can help that.
Yep.
But okay.
Practice and essentially, yes, you do have your own preferences or let's say preferences in the design process or the development process where one person focused on one part, but overall, all of you need to be semi-proficient in every aspect of your design. So technically, when you split that, what you're given, like you're presenting about the design, you should be able to talk knowledgeably about it, especially if you have the presenter's notes, which the whole team can help write, and you can just help present with those.
All right.
Yes, any more questions?
April, what questions do you have?
No questions. Good job, guys.
All right. Cool. Okay. Well, we're a good 10 minutes over where we were supposed to stop. So, but
There's no more sessions after this one today, so.
no, that's true. We can just keep going if you want. I'm sure these guys have other things to do. Plus, there's I think a final design report deadline coming up in a couple hours. So, okay. So let's wrap it up there. So my kind of final parting thought comment is just to thank you guys one last time for sharing your presentation with us this evening. You guys happen to be the last group, but last but not least, I want to just in general thank you for your creativity and energy and coming to class and putting up with me all semester. I hope that you guys got as much out of the class and had as much fun taking it as I had teaching it. And I look forward to seeing, hopefully most of you in Mech 3 next semester in the near future. So just want to thank you guys for a good semester. This class, John Brooks isn't here, but John Brooks calls Mech 2 the the final boss in the mechanical engineering curriculum. So you guys have, well, you're what, 4 hours away from defeating the final boss in the curriculum, at least according to Professor Brooks. So well done.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
All right.
Good
Uh,
job.
Okay, let me hit the record stop button.